We're finishing up related rates problems today. The first day we had some general examples that weren't even really word problems, just how to go through the process without the X's and Y's really standing for anything. And then yesterday we got into some word problems, and the word problems that we did had to do with volume or had to do with a right triangle. Some of today's are right triangles too. And I want to show you one thing I put in momentum for you. Let's read number 26 and then I'll show you what I put in there. An airplane is flying at an altitude of 5 miles, passes directly over a radar antenna. Is that anything about the following sentence tells you that 5 miles changes, or is that plane going to maintain an altitude of 5 miles? Maintain. All right, so that's a constant. If it's a constant, we can put it on our picture. Here's my very best airplane going that way. Going that way, which I should know what direction that is, but I'm just going to say to your right. This is the altitude of that airplane. And a few minutes ago, it passed directly over a radar antenna. You want to see my very best radar antenna? There it is. All right, an airplane is flying at an altitude of 5 miles and passes directly, or did pass over that radar antenna. When the plane is 10 miles away, the radar detects that the distance between the plane and the radar is changing at a rate of 240 miles an hour. Do you see the distance between the plane and the radar? Hypotenuse of a right triangle right there. And when the plane is 10 miles away, is that a constant or something that's changing? So I'm not going to put it on my picture. The radar detects that the distance between the plane and the radar, sounds like we need a variable for the distance between the plane and the radar. You have a favorite variable for that distance? What about D for distance? That's fine. Any, mini, miny, mo, pick your favorite variable. D for that distance. The distance between the plane and the radar is changing at a rate of 240 miles an hour. What is the speed of the plane? Now, I tell you what, this is a good time to show you what I put in momentum for you. Sometimes I have a hard time visualizing movement. I really can picture things that are standing still, but not things that are moving. And so I found these animations and put links to them in momentum under the test 3 notes. There's a link for related rate animations. And this one is the air traffic control, not the same numbers, but a problem like it. All right. You see down here is my antenna. Here's my plane. And watch what happens to the length of this hypotenuse. That's what we call D, as the plane continues to fly at an altitude of 5 miles an hour. Obviously, as the plane's distance from its original point increases, its distance from the antenna also increases. But what on that picture would have anything to do with the speed of the plane? It's the horizontal speed. It's how fast it's flying this way. So we need a variable for, can't see both at once. We need a variable for this horizontal distance, and that differentiated with respect to time, dx over dt, that'll be the plane speed. So let's let x be this horizontal distance. And then we're asked, what's the speed of the plane? That's how fast x is changing with respect to time. So what symbol will we use? What related rate symbol will we use for the change in that distance with respect to time? Dx over dt. Good. Actually, that's what we're looking for. Dx over dt. And what is that rate of 240 miles an hour?
That's big D over D.
All right, that's the change in this distance per hour. So that's d of capital D with respect to t. That's the 240 miles an hour we were given. The speed of the plane is the change in x with respect to time, and we're supposed to find that when, what's this other number we're given? Do I need another variable or y?
The plane is 10 miles away. So
10 miles away from what? Is it x being 10 or is that d being 10?
X.
10 miles away from what? From the radar. 10 miles away, or 10 miles away from the radar. So that's when big D is 10. Now I think drawing the picture and writing that sentence is the hardest part. If you can identify the quantities you're given and the quantity you're looking for, then I think you could come up with an equation, especially since that's a right triangle. What equation would relate my x's and d's in this problem? Leg squared plus leg squared equals hypotenuse squared. And once we have that equation in terms of only the variables that were given or the variables that we're looking for, let me say that better. The rates that were given or the rates that we're looking for, then we can differentiate. So differentiate both sides with respect to time. Left-hand side, 2x times dx over dt plus derivative of 25 is 0. I don't even have to write that down. And the derivative of the right-hand side with respect to time would be 2d dd over dt. And we're looking for dx over dt. I can either substitute numbers now that I've differentiated and then solve for dx over dt, or this problem, it's really easy to get the dx over dt by itself before I substitute the numbers. So it doesn't matter which one you do. I think if you look at CalcChat, and try not to, but if you get absolute stuck and you have to look at CalcChat, you'll notice them doing problems in lots of different ways. Sometimes they solve for the variable they want before they substitute any number. Bless you. Sometimes they substitute numbers and then solve for the quantity. Sometimes they have their variables or their sketch labeled differently. But if you come up with the right answer, then the way you were thinking about it is just as valid as the way the author was thinking about it. Like I said, since it's easy to solve for dx over dt, I will just divide both sides by 2x, and I'd have d over x times d over d, or d, hard to say, little d, big D, with respect to t. And now I can substitute those numbers. I can find dx over dt when d is 10. Now, how many quantities do I have to substitute into the right-hand side of that equation? I think 3. I have a d, I have an x, I have a d over dt. I know the d, I know this, I don't know the x. Where am I going to get that x? Pythagorean theorem, when x equals, no, when d equals 10, substitute that into our original equation and find out what x is. x squared plus 25 would equal 100. B squared 100. So subtract 25 from both sides. And take the square root of both sides. Why do I not need a plus or minus here? Yeah, we're talking about a distance, and a distance can't be negative. So x is the square root of 75, which you can simplify or not. You're going to eventually end up getting me a decimal approximation of that answer. I found it easiest if I went ahead and said 75 is 25 times 3 and take the square root of the 25, just leave the 3 under the radical. It allowed me to simplify that expression more easily. So now I'm ready to find the speed of the plane when d is 10, x is 5 square root of 3, and the rate of change in d with respect to t is 240. That ends up being 480 divided by the square root of 3. That's the exact answer. If I don't specify on the test, and I'll try to specify, but if I forget, I'll take the exact answer or a decimal approximation rounded to whatever you feel is appropriate. All right, but I'll try to remember to give you directions like give me the exact answer or give me the answer rounded to the nearest whole miles per hour. To the nearest whole miles per hour, I got 277 miles an hour. So that was a lot like some that we did yesterday, in that it involved a right triangle in the Pythagorean theorem. Any questions on that one? All right. I think number 28's a little more interesting. I had to squint a little bit harder the first time I did it. I have an animation for this in Momentum also. A baseball diamond is the shape of a square with sides 90 feet long. Suppose a player is running from first base to second base at a speed of 25 feet per second. All right. What is it?
What's your running 25 feet?
I have to think hard about, oh,
It's so
that is really possibly supposed to be a minute. Because 25 feet a second is flying. All right, let's change it to a little bit more realistic. Let's make that per minute. Nobody had ever noticed that before. Miguel, I like it. I like that you realized dude's on fire. Okay. Let's look at this animation. For the baseball diamond. Another thing that I realized that I used to not realize when I gave a word problem on a test, I have to be careful to give you all the information to solve the problem, even if you don't know anything about the subject. Even if you don't know anything about baseball, I need to tell you that there's 90 feet between the bases, and I probably need to tell you which base is home base, first, second, and third, just in case you don't love baseball, you can still solve the problem. All right, here's my animation. Now in this one, we have dude or dudette running from home plate to first base. And notice, see if I can drag. No, I can't drag that. I need to just hit play. Notice that as the player gets closer to first base, what happens to his distance from second base? It's getting smaller. So as his distance from the first base gets smaller, his distance from the second base also gets smaller. If you're having any trouble visualizing these, picturing what's going on, you might want to click on these animations tonight. Yes, ma'am.
You said somebody was getting smaller spots.
I'm not sure what I said. What I meant was, as the player's the red dot, the runner is the red dot. And as that red dot gets closer to first base, as that distance gets smaller, his distance from second base also gets smaller. Some problems we're talking about his distance to first base and his distance, his distance as he's running from first base to second base, what's happening to his distance from home plate. So this is just one particular scenario. It's not even the scenario in this problem, but it helps you picture somebody moving and how distances are changing as that person is flying at a rate of 240 feet per second. Or that was the airplane, 25 feet per second. 25 feet per second. All right, he just blew up. He just blew up. Okay. If I assume that you're not a baseball fan, then I would probably draw a baseball diamond for you, or the problem tells you it's a square. So play like these are 90-degree angles. It's a square turned on its side. This is home right there. Here's, yeah, it's a square, and so those are supposed to look like right angles. That's first base, second base, third base, and then back home. That's my very best baseball diamond. And is that 90 a constant or something that's changing? Unless somebody's moving the bases, that's a constant. So I'm going to go ahead and put it on my picture. Any one side, all four sides are 90 feet long. All right. Suppose a player is running from first base to second base. Here's my very best player. Between first base and second base. Find the rate at which the player's distance from home plate is changing. And you dash in a line that would show the player's distance from the home base. Right there. And again, whether it looks like it or not, that is supposed to be a right angle. All right. Find the rate at which the player's distance from home is changing. Sounds like we need a variable for this. What can we call that? Big D for distance again? Sounds good to me. That's D. If this side is 90, well, we were told all sides are 90. So let's go ahead and call that 90 right there. And what else do you think we need a variable for? What is that 25 feet per minute?
Yeah.
Well, it depends on where I put X. What's that? X is. Thank you. I need words. I need words, not pointing. The words are X can either be how far he is from second base or how far he is from first base. Doesn't matter. It's you label your picture however you want. If I label X the distance from second base right here, then I'm going to have to say that distance would be what? 90 minus X. So it may be easier just to call this X, since that would give me labels for all three sides of a right triangle. But I could have called this X. Any, mini, miny, mo, up to you. All right. What is this 25 feet per second? What's the symbol for it? That's how fast X is changing. So dx over dt is what we're looking, what we're given. Dx over dt is 25. Give me the symbol for the rate we're looking for. All right. dt over dt. And then what other quantity are we given? Find that when 20 feet from second base, is that the X or the?
That's the other side. Is that the distance from the second base?
That's distance from second base. And what we decided was to let X represent the distance from first base. So if the distance from second base is 20, what's his distance from the first base? 70. Read that carefully. That's why you have to label your pictures. If you call this X, what I've labeled X, then that's not the 20, that's the 70. Read carefully. That was the hard part. What equation would relate my X and my D? Leg squared plus leg squared equals hypotenuse squared. And don't plug any numbers until after you differentiate. 2x times dx over dt plus 0 equals 2d derivative of d with respect to t. Which one of those quantities are we looking for? We're looking for the derivative of d with respect to t when x equals 70. And I can either substitute the numbers I have and then solve for dd over dt, or I can solve for dd over dt and then substitute numbers. If it's easy to solve for d, the derivative of d with respect to t, I just go ahead and do that. Divide both sides by 2d, and you have x over capital D times dx over dt. Now, how many variables do I have on the right-hand side? 2? No, I have 3. The quantity dx over dt is a variable also. So I have an x, a d, and a dx over dt that I need numbers for. I have an x, I have a dx over dt, I don't have d when x is 70. How do I find d when x is 70?
Plug in
Into the original equation or into the Pythagorean theorem. When x is 70, then 70 squared plus 90 squared equals d squared. And that's 4,900 plus 8,100 equals d squared. Or d squared equals 1,300.
13.
Did I not have enough zeros? That is almost 5,000 and 8,000. Yeah, 13,000, not 1,300. And if you want to simplify that, well, need one more step. D is the square root of 13,000. And if you want to simplify that, you can write it as 100 times 130. and take the square root of the 100, just leave the 130 under the radical. Really doesn't matter if you simplify it or not, as long as I'm asking for a decimal approximation. But as it did here, it may make the math easier without the calculator if you simplify your radical expressions. All right, now I have an x, I have a d, I have a dx over dt, and I'm ready to finish this. d over dt, the derivative of d with respect to t is this x, which is 70, divided by this d we just found, 10 square root of 130, times the rate of change in x we were given is 25. I just said 10 goes to 7, be 7 times 25 is 175. And that is what I punched on the calculator. Square root of, no, 175 divided by square root of 130. Got darn close to, if I say round to the nearest hundredth, it would be 15.35. What's the units on that 15.35? If we change that seconds to minutes, then this is feet per minute. All right. Hardest thing about that one was just picturing the baseball diamond and getting it labeled with whatever variable I choose. But I've got to read real carefully. If I let this be x, then I have to realize that what I'm given, 20 feet from the second base, is not the x, it's this distance. And that's why I had to subtract to get the value of x. All right, number 30 is another one that it might be good to see an animation for. A man 6 feet tall is walking at a rate of 5 feet per second toward a light that's 20 feet above the ground. Here's my very best light. It's 20 feet above the ground. Is that a constant or something that's changing? That light is always 20 feet above the ground. A man's walking toward that light. Here's my very best man. Walking toward that light. And is his 6 foot tall height something that is constant or changing? I hope it's constant. His height up to the tippity top of his head is 6. I don't. I have to assume that the person telling me his height is giving me the truth. All right. If this light is shining down on Dude, is Dude's shadow going to be behind him or in front of him? It's going to be somewhere over here, right? Let's draw that. Let's say as that light is shining down, then the tip of his shadow is going to be right there. As he's moving toward the light, is his shadow going to be getting longer or shorter? If he's standing right below the light, is he gonna have a very long shadow or a very short shadow? Very short shadow.
Yeah.
And that's why I put some animations in Momentum for you. Miss Peter Pan knows that when he's right here, the shadow's gonna be practically nothing. And so as he walks this way, the shadow's getting shorter. If that's difficult for you to visualize, then lucky for you, you have me. Lucky for you, you have me. Here's shadow length. I don't think I have a play button on this one. I think I can just move. Let me see. It's zoomed in too much. I think I can move skateboarder dude.
Or just click. The click here for relate.
I actually have to drag this time button. Okay. Now, notice as this guy is going away from the light, and as Miss Abigail predicted, if he were going away from the light, his shadow would be getting bigger. Yes, longer. As he's skating back toward the light, his shadow is getting shorter. So now I better understand what's going on with the picture. Okay. Let's go back to our problem. Actually, this one has an A part and a B part. We haven't finished reading this though. A man 6 feet tall is walking toward the light that is above at a rate of 5 feet per second. What do you think we need a variable for so that we can give meaning to that 5 feet per second?
His distance.
Okay, let's call this, even though I have him standing right there, let's call this his distance from the light. So call that X. And then what could we use as a label for that 5 feet per second? Sounds good. Given dx over dt is 5 feet per second. Now in the A and the B part, we're looking for two different things. In the A part, we're looking for the rate at which the tip of his shadow is moving. What would that be in relation to my picture?
Between the 6 and the
Between this and this?
Yeah.
That's not how fast the tip is moving. That's how fast the length is changing. And that's actually what the B part asks for. If we're saying the rate at which the tip of his shadow is moving, if dx over dt is the pace at which his feet are moving toward the light, then we need something for how fast that shadow is moving toward the light. Right now, that tip of the shadow is y feet away from the light. We want to know how fast that's changing. Now, this is not the only way you can label the picture. This is the way it makes sense to me. All right. So if we're using these labels, what is it that we're looking for? What symbol? That's the rate at which this distance is getting smaller. Ooh, I just thought of something else when I said distance is getting smaller. What does that tell me about dx over dt? If this distance is getting smaller, I need to let it be negative. And do I expect dy over dt to be negative or positive? If X is getting smaller, Y is getting smaller also, because he's walking toward the light, his shadow is also moving toward the light. So I expect to get a negative for that. All right, the A part says, when he is 10 feet from the base of the light, what variable does that correspond to? That's X. Find dy over dt when X is 10. Think we have it?
Yeah.
All right. What about an equation?
Would you do like the similar triangle things?
Yes, exactly. I can't use the Pythagorean theorem because I don't know anything about the hypotenuse here. But I have a baby triangle within a big triangle, and that's when I can use similar triangles. And there's different ways you could set up this equation. I like to set up my similar triangles as little is to big, as little is to big. My little triangle being the yellow one, and the big triangle being the green one. So if I say little is to big, I could say this 6 is to this 20 as what? Ooh, I've got to have this side of the little yellow triangle, and if this side of the big triangle is y, and this part of it's x, then this is y minus x. Could you give me words for what y minus x actually represents?
The length of the big triangle.
I'm talking about in respect to this problem, not just my picture. That's the length of his shadow. I didn't ask that well enough that you knew what I was asking. The length of the shadow. So 6 is to 20 as what? Little is too big. Y minus x is to y. Just need an equation that involves x's and y's, because those are the quantities I'm given or the quantities I'm looking for. I could either differentiate the right-hand side with the quotient rule, or I could do some simplifying there. I could cross multiply. 6y equals 20y minus 20x. If I distribute that 20. So 14y equals 20x, or y equals 10/7 x. A little bit easier to differentiate y equals 10/7 x than differentiate that with the quotient rule. But we get the same thing. Differentiate both sides with respect to t. We have the change in y with respect to t equals what on the right-hand side?
10/7 dx over 20.
Yep. Any questions?
Whatever the heck.
What's the derivative of x?
I know that, but don't we have to have something, an x term at the end to plug x equals 10 into?
But we don't.
So is it
Because the rate at which this shadow is changed, the tip of the shadow is moving, doesn't depend on how far the guy is from the light. It only depends on how fast he's moving. But how fast the shadow's moving is 10/7 times the rate at which he's moving, regardless of how far he is from the light. So I can't just throw in an x because I think an x ought to be there. I need to say the derivative of 10/7 x is just 10/7 dx over dt. All right. Do I have everything I need to substitute in that equation to find dy over dt?
Yeah.
Yeah, all I need to substitute to find dy over dt when dx over dt is -5 is 10/7 times -5.
Yes. Yes.
Wouldn't what suggest that? I'm still not understanding what you're saying. Oh, you're saying, do I need the word when there? It's okay to use it. But if somebody says, when is dx over dt -5, I'm gonna say all the time. Yeah, it's always -5. So 10/7 times -5 is -57. And what's the units on that? Feet per second. I just left that a fraction. The B part says when he is 10 feet from the base of the lot, at what rate is the length of his shadow changing? Well, what symbol can we use for the rate at which the length of his shadow is changing? The length of his shadow is given by y minus x, the way that I labeled my picture. So d of y minus x over dt is what we're trying to find. Find dy over dx, or d of y minus x over dt when x equals 10. Do I need a different equation? I mean, how do I find dy over, or d of y minus x?
Use.
Can you take derivatives term by term?
Yes.
So how could I find d of y minus x?
Sure.
D of y with respect to t minus dx with respect to t. The rate at which his shadow is moving, we just found that to be -50/7. The rate at which he is moving is -5. So -50/7 plus 5 is how fast his length of his shadow is changing. And I got that to be -15/7 and don't have room to write feet per second. So yeah, you can take derivatives term by term. So you can find this by finding the difference in those two derivatives. All right. I wanted to have time to do 2 more. I'm only certain that I have time to do 1 more. Any, mini, miny, mo.
We already did it.
But this is different. Both of number 40 and 42 are asking something about an angle of elevation. I tell you what, we may set up both of them, but not finish them. And that way we'll at least have an idea of how to set up these angle of elevation problems. All right, number 40. My very best balloon. Well, let's start with my very best balloon. And my very best flat ground. A balloon rises at a rate of 4 meters per second from a point on the ground 50 meters from an observer. You see where the observer is? Here's the point on the ground directly beneath the balloon, right there. Here's my observer. Right here. Hey, I forgot to mention this earlier, but something I found to be helpful, and I've been doing it without pointing out that I was doing it. I started using solid lines for things that don't change and dashes for things that do change. Now, if I had followed that precisely, I would have a dash line for X because that's changing, but this 5 is constant. This 90 is constant, but that distance is changing and that distance is changing. I wish I'd used a dash line for that. It just helps me keep straight what's changing and what's fixed. Is that 50 meters something that's changing or fixed? Yeah, he's not running toward the spot where the balloon was released. It's always 50. The height of the balloon is changing though. And so that's why I have it in a dash line. A balloon rises at a rate of 4 meters per second from a point on the ground, 50 meters from an observer. Find the rate of change of the elevation of the balloon from the observer when the balloon is 50 meters above the ground. Do you see where the angle of elevation is? Remember, angle of elevation is always, always, always with respect to the horizontal. It's how much dude or dudette has to crank his head back to see the balloon. That's the angle of elevation right here with respect to the horizontal. And let's just call it theta. Now, what variables do I need? What's that 4 meters per second? It's how fast this is changing. So what can we call that? H for height is perfect. I was thinking Y is usually a vertical component, but I like H, that works. What symbol could I use then for the rate of 4 meters per second? What is that? That's the rate at which H is changing. So dH over dt is 4 meters per second. Give me a symbol for the thing we're trying to find.
Yeah.
D of theta over dt. When what? When the balloon is 50 meters above the ground, that's when H is 50. Need an equation relating H and theta. Ooh,
Sine.
give me the whole equation. Y'all are right to be thinking trig.
But sine. H-O.
Is that what sine is? That's what tangent is. Tangent's opposite over adjacent. So what's my equation? Tangent theta equals H over 50. You might want to multiply both sides by 50. You don't have to, but it just makes my equation look a little neater. H equals 50 times tangent theta. So what's the derivative of the left-hand side with respect to time? dH over dt. What's the derivative of the right-hand side with respect to time? Awesome. 50 secant squared theta times d theta over dt. Very good. Right? If I'm solving for d theta over dt, then I need to know dH over dt, which I do. but I also need to know what theta is so I can take secant squared theta. How am I gonna find out what theta is? The hypotenuse is not anywhere in this equation.
Yeah. Inverse, yeah.
Okay, you know what? I don't actually have to know what theta is. I just have to know what secant theta is. So let me fill in this blank right here. Find d theta over dt when h is 50. I can say when h is 50, then this triangle becomes, that height is 50, this distance is always 50, and there's my theta. Yes. It doesn't look like it on my paper, but these two are supposed to be the same. What can you tell me about theta? Yes, yeah. You can pull something from geometry and go, oh, that's an isosceles triangle, right? That has to be 90, so that has to be 45, that has to be 45. That's fine. Now that I get where you got that. That wasn't how my brain was working. My brain was saying tangent theta equals 50 over 50, or tangent theta equals 1. You're going to get the same answer. You can either use 45 degrees or you can use pi over 4 radians. Doesn't matter.
I was thinking solve for the hypotenuse and secant. That worked too.
Solve for the hypotenuse. You could solve for the hypotenuse, and then you could say secant is hypotenuse over adjacent. That would work also. And that's how it's going to be when you look in the solutions manual. It's going to be a different way, quite possibly a different way than you thought about the problem. You just have to go ahead and finish yours and see. Hey, we are about to run out of time, but here's what I'm going to do just for video purposes. I need number 42 on the video, and y'all might need to see number 42 when you get home. So after I finish 40, I'm going to hang around to video number 42. If you want to hang around, you may. If you need to go, go. It's okay. But I think I have time to finish this one real quickly. If I'm solving for d theta over dt when h is 50, I know dh over dt is 4. I know 4 equals 50 times secant of pi over 4, whatever that is, squared, times the thing I'm looking for, d theta over dt. And secant of pi over 4, if you find secant of pi over 4, it's just square root of 2. So if I divide both sides, no, let me put in the middle step. Square root of 2 squared is just 2, and 2 times 50 is 100. Yes.
Could you, like, originally in the question, like the secant square, could you look back at the other triangle and do like 1 over the cosine of it?
Yeah. lots of different ways to think about it. How I did it's okay, how you just you just described as fine, Rachel's idea was fine, Madison's idea was fine. We're all thinking about it differently, but coming up with the same thing.
Just wanna make sure.
Yeah, yes. All right, I'm gonna hang around and do 42 just for the video. Yes, sir, Austin? I knew, okay, let me tell you something funny. Oh, I don't have time to tell the whole story. I emailed a colleague last night and said, please help me come up with the words for why that's radians, because I know Madison's gonna ask. I'll have to email her and say, actually, it was Austin who asked. Remember, radian is the ratio of an arc to the radius of a circle, and if they're both in feet, then the units cancel. Radians don't have units. If you just say find the sine of pi, you don't have to say pi radians. You just say sine of pi. Radians don't have units. This is, okay, let's just say she didn't email me that yet. I was trying to come up with those words. No, and that's what I said in my email last night. I could have used theta equals pi over 4. And then it kind of made sense why this is radians per second. But if I had used 45 degrees, well, the secant of pi over 4 is the same as secant of 45 degrees. I would have gotten the same answer. The unit still would have been radians per second because, and here's where I'm just gonna wait till I talk to Jillian about it. Jillian and I will have lunch and have a big discussion, and we both love math so much. But it has to do with the fact that radians, the measure radians are unitless. It's a ratio of an arc to a radius. Several years ago, I asked Jill Denton the same question. She's retired now, and she said, change of elevations always radians per unit of time. And I said, that's not going to be good enough for Madison. I'll say that won't be good enough for Austin. All right.
Austin and Madison.
Austin and Madison and everybody who wants to be precise. All right. I'm going to do 42 for video's sake. Number 42. See you. Y'all have a great weekend. I am going to take up the rest of the homework day 2 and day 3 Mondays. 42. An airplane flies at an altitude of 5 miles toward a point directly over my observer. So I have an observer. Right here. And I have a plane flying toward a point over the observer. So here's the point over the observer. I have a plane flying toward that point. Right? What about that 5 miles? Is that a constant or something that's going to be changing? Yes, that plane is maintaining an altitude of 5 miles. The speed of the plane is 600 miles an hour. And this person's going to be looking up at the plane. If I was staying true to my dash line thing, then I would have made the plane's path a dash line also, because that's changing. And the angle of elevation, remember, angle of elevation has to be with respect to the horizontal. So it can't be this angle. That's not with respect to the horizontal. This is with respect to the horizontal. Or you could imagine the ground here and say that is respect to the horizontal. Well, guess what you know about two parallel lines cut by a transversal alternate interior angles are the same. So we can either call this theta or we can call this theta. I'm going to call this one theta because it's inside my picture, and it makes more sense to use something inside my picture than something outside my picture. But you need to understand why it cannot be this. That's not with respect to the horizontal. All right. So it seems like I need one more variable. Any ideas? Because right now all I have is a 5 and a theta.
The angle of elevation changing, is that the way he's looking like? It's
Yes, how much he or she is cranking his head back. So it's directly over him. He's staring straight up.
With his feet looking at it, like he's laying on the ground.
Yes, yeah. And that's why I'm illustrating dude with a dot. Okay. In my picture, it looks like dude is buried, standing up vertically below ground. That is not the case. He's just that dot. So I need another variable. What does this variable need to represent?
Speed of the plane, we said.
Okay, I have a 600 that I don't have a variable for. It's the speed of the plane. What's
The distance from the fog altitude of it. Or that above the person.
the distance that the plane has traveled?
Yeah.
So it's this horizontal distance is x. And I'll just make a note here. So dx over dt is the speed of the plane. If you call it speed of plane, you may be thinking, why? Why is that the speed of the plane? But if you think about it as the change in x, how x is changing with respect to time, then that makes sense. That's why that's the speed of the plane. That's exactly what speed is. So the speed of the plane is 600 miles an hour. Sounds like we're given dx over dt is 600. What's the symbol for the rate at which the angle of elevation theta is changing?
D theta over.
Find d theta over dt when, what's the other thing we're given? When theta is 30 degrees. I need an equation relating x's and thetas.
Tangent.
Tangent again, tangent theta would be what? Would it? 5 over x, opposite over adjacent. So tangent theta equals 5 over x. Oh, I left out my theta. Tangent theta equals 5 over x. If I clear out fractions here, then I'm going to have to use the product rule to differentiate that. But if I don't clear out fractions and just think of it as tangent theta equals 5 x to the negative 1, then I can just use the power rule. Derivative of the left-hand side would be secant squared theta. Anything else? Times d theta over dt. And the derivative of the right-hand side would be negative 5 x to the negative 2, or I could write it negative 5 over x squared. Anything else?
Dx over dt.
Dx over dt. I'm solving for d theta over dt. And if I wanted to go ahead and get it by itself, how could I get d theta over dt by itself? And what's the same thing as dividing by secant squared?
Inverse.
Same thing as dividing by secant squared. multiplying by cosine squared. D theta over dt will be -5 over x squared times cosine squared theta times dx over dt. Now, if we were all working this at home, we might have all labeled our pictures differently. We may think about a different way to finish the problem. I'm given a value of theta. I'm given a value for dx over dt. I don't have an x. So I'm gonna have to find an x when what?
When the tangent of 30 equals 5 over that.
Okay. Let me fill in my blank and then finish
Oh.
what you're saying.
That's what-
Well, I asked that question before I was ready for it. What I'm ultimately looking for is find d theta over dt when theta equals 30 degrees. In order to do that, I have to find an x when theta is 30 degrees. And I find x when theta is 30 degrees.
Plug in the 30 theta and then in the original equation,
Into this equation,
the tangent of 30 equals 5 over x.
okay. That's a perfectly good way to do it, 100% fine. I thought of the unit circle when when theta is 30 degrees. Oh yeah. 30 degrees on the unit circle, what's x? Square root of 3 over 2. Be your x. But what you said would work just as well.
It'd be a lot easier if it's all.
I think we have everything now to plug and chug. D theta over dt is -5. Something is bugging me.
Yeah, I'm trying to remember.
Yes. Something is bugging me. I love it when I make a mistake at the very end. You can't assume that this is on the unit circle. You don't know that radius right there is 1. So that's not necessarily that we could use that to find cosine squared theta, but we're going to have to do what you said, Carrie, to find x when theta is 30 degrees, because we can't assume that that radius is 1. So that is one thing we need to know, but the thing we also need to know is tangent 30 degrees equals 5 over square root of x. We need to solve that for x. Now, it's still helpful to me to have this picture. What is tangent of 30 degrees?
Square, no tangents.
The y divided by the x. So you would flip the x. Yeah, it actually what I did was yeah, I'm gonna go ahead and just 1 over square root of 3, the y divided by the x, and then cross multiply the proportion. X equals 5 square root of 3. So let me erase one thing that's a little bit confusing right here. That looks like I have 2 different values of x. I did need to think of that ordered pair so that I could find tangent 30 degrees and use it to find X. But the X was not simply that X value right there. What can I put in the place of cosine theta?
30 degrees.
Or cosine 30 degrees. I've already put 30 degrees in the place of theta. What can I put? Let me just write this middle step. Cosine 30 degrees squared over 5 square root of 3 squared times that 600. After that, it's all numeric. Cosine of 30 degrees is square root of 3 over 2. I need to square that. Square the denominator. And I'm just going to say dot, dot, dot. I ended up with 30 radians per hour. It took me a few more steps of simplifying, but it turned out to be 30 radians per hour.
Is that the exact?
That actually was exact. It came out to be a whole number. How does that come out to be 30?
Yeah. I got negative 75.
Yeah.
Yes, it will be negative. I did get a negative. I was just running out of room. Let's see. -5 times 9/4 times. Oh, it is 3/4, absolutely. -5 times 3/4 divided by 75 would be, I could say 4 goes into 600, 150 times. So that is -5 times 450 divided by 75. Is that right? 4 goes into. Yeah, that's right. And then that's right. And then what does that turn out to be? Is that not 30?
Yeah, it is 30.
Okay.
Yeah, I get 30.
Okay. All right, that was the hardest one because that was the last one, and the last one's always the hardest one. Y'all have a great weekend, and I'll see you Monday.